Today, we want to continue convincing ourselves that we are awesome at calculus and demonstrate what we know by finding some partial derivatives. We're going to work on some mechanics today, and we're going to show ourselves that we have lots of mechanical skills that we just need to upgrade to Calculus 3 multivariable calculus. So, yesterday we introduced the concept of the partial derivative, dz dx, or fx, and dz dy, or fy, modifications of our earlier notations. The phrase I'm going to use is, I want to refer to the other variable. So if we're taking the partial of z with respect to x, then y is the other variable. And in the partial of z with respect to y, then x is the other variable. The main thing that we have to learn is that the other variable is either a constant term or a constant factor. So constant term, the derivative is going to be 0. A constant factor just gets carried along. The derivative of a constant times a function is that constant times the derivative of the function. To that end, we have 10 functions here. So there's going to be 20 partial derivatives for us to find. So pause the video here, take a moment, and find these 20 partial derivatives. Then we'll come back and have some commentary on each of them. Welcome back. Let's take a look at some of these these functions and find their partial derivatives. I just want to make some commentary on a few of these functions, starting with the first one, where f of xy is x cubed times y to the fifth. In this case, the x and the y are being multiplied together. X to the third and y to the fifth are being multiplied together. So the other variable is going to be a constant factor. So y to the fifth is a constant factor with respect to x. Y to the fifth is a constant factor in fx. And then for fy, x to the third is a constant factor x to the third is a constant factor in fy. So when we take our derivatives, we'll take the derivative with respect to x, which is 3x squared, and y to the fifth is a constant factor. It just gets carried along. So we get 3x squared, and then we just keep the y to the fifth. For our other partial derivative, fy, x to the third is a constant factor. We'll take the derivative of y to the fifth, which is 5y to the fourth, and just multiply by the x to the third. So fy at xy will be 5 y to the fourth times x to the third. We looked at how the x and y are included, and they're included with multiplication, so they're constant factors when they're the other variable. We can compare that to problem 2, where we have x cubed plus y to the fifth. So in problem 2, it's the other one. Here, the y to the fifth is going to be a constant term in the fx derivative, and the x to the third is a constant term in the fy derivative. So y to the fifth is a constant term in fx. And similarly, x to the third is a constant term in Fy. So that means the derivative of x, the derivative of y to the fifth, when we're taking the derivative with respect to x, is going to be 0. So Fx is just going to be 3x squared. I'll write it in the alt color. We wouldn't need to write plus 0. I want to demonstrate that the derivative of y to the fifth, when we take the derivative with respect to x, is going to be 0. Similarly, when we take the derivative of x to the third with respect to y, x to the third is a constant term. So the derivative is 0. And then the derivative of y to the fifth with respect to y is 5y to the fourth. In practice, all we would write is the 5y to the fourth. But I want to remind us that we took the derivative of x cubed with respect to y and came up with 0. Any questions? That's the core concept. The other variable is a constant term or a constant factor. How's everybody okay? So it's really important to separate in our mind. One of the reasons I didn't just write down the function, I wrote down f of x, y, is that we don't want to get this confused with implicit differentiation. I probably shouldn't even bring it up. Most students are very successful at wiping implicit differentiation from their minds after Calc 1, at least after the Calc 1 final. Some students wipe it before the final, as I can see on the final exams, but that's beside the point. So you don't want to look at x cubed y squared. Think of y as a function of x and start using the product rule. X and y are both independent variables in this context. So it's important that we remind ourselves of that by continuing to write the of x, y part. Or at least just keep that in the forefront of our mind, that we're finding partial derivatives. We're not trying to find dy dx. We're not thinking of x and y as being in a relation. X and y are both independent variables. The only other one I want to look at is number 3, where we have x cubed y squared plus y to the fifth. So with respect to x, the y squared is a constant factor, but y to the fifth is a constant term. So conveniently, I did not give myself enough space to keep going. So full page just for one more example. This also means I have to remember what the function was. Even though I just looked at it, I mean, what's the chances that I'm going to actually be able to remember what the function was? So it was x to the third y squared plus y to the fifth. So when we're thinking in terms of fx, y squared is a constant factor in fx. But y to the fifth is a constant term. So I have a combination of the previous two for fx here. So fx is going to be the derivative of x cubed, which is 3x squared, times the constant factor y squared. The derivative of y to the fifth with respect to x is 0. It's a constant term with respect to x. In practice, we wouldn't write plus 0, but we want to remind ourselves what happened to the y to the fifth. When we switch over to fy, x to the third is a constant factor in fy. So when we find Fy of xy, the x to the third just gets carried along because it's a constant factor. This is what we do with constant factors. And we take the derivative of y squared, which is 2y. We go to the next term, it's y to the fifth. The derivative of y to the fifth with respect to y is 5y to the fourth. So here we had the y part included as a constant factor in one place and a constant term in the other. That's the core mechanic for dealing with partial derivatives. The other variable is either a constant term or a constant factor. Mechanically, what we're thinking about is when we're looking at fx, if x is this direction, I know you can't see me pointing on the video, but that's okay. If x is along this wall and y is along the wall with the board in it, what we're doing is we're looking at how the function is changing with respect to x. We're only looking in this direction, so we can choose a fixed y value, a constant value of y, and just look at how z is changing in the x direction. So when I scoot over to this point, then we see how z is changing in the x direction again. Since we have a constant term, let's say plus y to the fifth, when I move side to side, that doesn't affect how z is changing with respect to x. We do care about the y squared, because when I move to this point, I'm looking at how things are changing here, and the y value is going to have an effect. And the y squared is going to be a constant multiple. So think in terms not only of the mechanics, constant term or constant factor, but how those holding one value constant, one variable constant, affects or doesn't affect how z is changing in the x direction or the y direction. Any questions? After that, it's just a matter of escalation. We just start adding more things, but all the other things are the same. Product rule, quotient rule, chain rule. So if we look at sine of x cubed y to the fifth, we have a composition of functions. Derivative of sine of something is cosine of that thing times the derivative of that thing. And that derivative would be either the fx or the fy. Similar in problem number 6, this is chain rule. In problem 7, I've got an x cubed and a sine of y to the fifth. In this setup, x cubed for fx, x cubed is the function, sine of y to the fifth, that's all just constant factor. But in problem 8, this changes everything. This x cubed changes everything. So now I've got a function of x times another function of x. But in problem number 8, when we think of x of fy, we think of the derivative with respect to y, x cubed is now a constant factor, and sine, this is the only function of y, sine of x cubed plus y to the fifth. It's all just a reading exercise. The other variable is either a constant term or a constant factor. Any questions? Just like me, to make you late for your 9 o'clock class. That's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.